A piece of rubber tubing maintains a cylindrical shape as it is stretched. So we have a rubber tube and we're stretching it out. At the instant that the inner radius of the tube is 2 millimeters, and the height is 20 millimeters, the inner radius is decreasing at the rate of 0.1 millimeters per second, and the height is increasing at the rate of 3 millimeters per second. And then we're given the volume of the cylinder. Which of the following statements about the volume of the tube is true at this instant? Now let's think about this. They're asking about the volume of the tube. We know that the volume of the tube is changing. This question is asking us about dV dt. It's asking us how is that volume changing with respect to time. And so in order to solve for that, we have an equation here that relates some of the other variables that we know. And why don't we make a table to outline what are the things we know and what are the things that we need to find. I like to put all my stuff into a box. I call it my known toolbox. We have our known toolbox, and in here, let's put in the values we know. I see that the instant we're talking about, the inner radius of the tube is 2 millimeters, so R equals 2. The height is 20, so H equals 20. The inner radius is decreasing, so dr dt, the radius, is decreasing at 0.1, so negative 0.1. And dh dt, the height, is increasing at a rate of 3 millimeters per second. Everything's in the same unit, so we can keep it as we see it. Now, what I'm noticing that we have to do next is we have to use this formula, V equals pi r squared h. And if we're using it, my hair's a mess, sorry. If we're using it, we have V equals pi r squared h, but the thing is, it doesn't say anything about dV dt. In order to do that, we need to differentiate both sides. When we do that, I'll do that in a different color. We get dV dt equals pi r squared h. That pi will come out, and then we do the derivative of this portion, r squared h. We have to apply the product rule, which I'll remind us is f, if we're doing this, f times g prime. That's going to be f prime g plus fg prime. This is our product rule. So we're applying that r squared. We want to find the derivative, so that's 2r dr dt times h plus, we keep that r squared the same. Now we find the derivative of h, which is dh dt. All right, now I'm going to distribute this. And so we get dV dt equals 2 pi rh dr dt plus pi r squared dh dt. And then, since we're asked to find dV dt, let's plug in the values that we know. I'll highlight this in a different color. We know dr dt, we know dh dt, we know h, and we know r. We know these values that are going to go in here, so let's plug them in. And I'm going to do that a little more over here so we have some more room. dV dt equals 2 pi times our radius 2 times our height 20 times dr dt, which is negative 0.1, plus pi times the radius squared. Our radius is 2, so 2 squared, times dh dt, which is 3. This shows us 2 times 2 is 4, times 20 is 80, times negative 0.1 is negative 8. So this becomes negative 8 pi, plus 2 squared is 4, times 3 is 12, plus 12 pi. And here we get 4 pi. And so since dV dt is positive, we found dV dt, we see that it's positive. This tells us that we are increasing. All right, that increasing because positive. And it's increasing at what rate? Well, we need the rate of this. dV dt, V is volume, so that's going to be millimeters cubed per unit of time, which is second. How do I know that? Well, I know that everything is in terms of millimeters, so my volume will be that unit cubed, and then per second comes from our rates. And so we see that our volume is increasing at a rate of 4 pi millimeters cubed per second.